Any questions from the previous lecture? No. So Curie and Pauli paramagnetism is clear to you. Okay, good. Now I'm asking because there was a slight problem at one place. I don't know if you spotted it. You must try to. It's a mistake of details, nothing very important. So now we come to module 4 of this course, where we will be dealing with again electrons, metals mostly, but now we will go beyond the free electron theory. We'll try to look at the band structure. Okay, so basically the broad theme of this module is band theory. All right. So I don't think I need to stress upon the failures of the free electron theory. There are many. For instance, by going from Druday's model to the quantum free electron gas, what we achieved is that we could explain the specific heat very nicely. The specific heat of metals, right, increases linearly with temperature, and uh, because of that, also the velocity at which the electrons move, which is of the order of 10 to the power 7 centimeters per second, right? We got it right from the quantum theory. But there are many other things that, many things actually that cannot be explained just by ignoring the lattice completely. So far we have ignored the lattice altogether. Of course, in Druday's model, we started off with by assuming that the electrons are scattered by the ionic cores, but that perception was clearly wrong, because we figured out from the experimental data that the mean free path at low temperatures can be of the order of thousands of the lattice spacing, and this cannot be possible if electrons really bombard against the ionic cores, right? So we had to give up on that notion. So at this moment, we don't know what role the lattice really plays, and this is what we are going to explore during these lectures. Okay. So if we go by just the free electron gas, of course, when I say free electron, I mean degenerate gas, which means that we have to deal with Fermi-Dirac statistics. It's not a classical gas. So for a free electron gas, we figure that the energy E is given by h bar square q square over 2m. Is that right? Where m is the mass of electron and q is the wave vector associated with the electronic waves, the waves of electrons. And you can plot it actually. So this is known as the dispersion of a free electron gas, because you're plotting omega versus k. Instead of k, I'm using q because we use k for phonons, right? So it will be a parabola. So this is how it's going to look like, right? And q extends from plus infinity to minus infinity. Do we know anything more about this q? What else do we know about this q? Is this q quantized? Can this q take any arbitrary value? No. We fix the values of q using the periodic boundary condition, right? And there we noted that q I is equal to 2 pi by L times some integer, let's call it S subscript I, right? Where I is, we can remove this subscript here because S belongs to set of integers. This S belongs to the set of integers, and I here is for X, Y, and Z. All three, each of these components are quantized. And what is L here? L is the size of your sample. So if you're dealing with three-dimensional solid, then it's a cube of edge L. If it is a 2D lattice, then it's a sheet, and if it is a 1D lattice, then it's just a 1D lattice of length L. So it may extend from minus L by 2, for instance, to plus L by 2, where L is some macroscopic dimension. L can be 1 centimeter. So 1 centimeter long 1D solid, something like that. This is our 1D model without taking the lattice into consideration. I mean, the only effect of lattice that we have taken is that it neutralizes the negative charges of electrons. So it's a uniform positive background, right? So if you like, let me just draw a 2D version of it. So the 2D version of it would be that you have this sample of sides L, okay, and then there are these electrons. All right, and the electron density is important. The electron density in 3D was little n. Here it will be n, little n as well, but it will be total number of electrons divided by the area of the sheet if it is 2D. Now, we are going to break this perception that there is no lattice. So here in the free electron model, there is no lattice, there is only a uniform positive background that neutralizes the charges of electrons. So you have a uniform positive background. Due to the lattice. But now we say that no, that's not correct, of course. We do have a lattice. So the structure looks very broadly looks like this. This is your lattice. And each of these lattice sides, there is an ion. So there is an ionic core. Right? So that's the correct picture. And that's the picture that we used in the free electron model. So basically, the Hamiltonian that we solved, the one electron Hamiltonian, in this case was simply h psi. So this was our energy eigenvalue problem. And here h is simply minus h bar square by 2m del square psi equals E psi. Okay, but in this case, the nature of the problem will change, and you will have minus h bar square by 2m del square psi plus V psi equals E psi. So now you have an additional potential energy term. But this potential has a very interesting property. Can you guess what that property is? It is periodic. Why? Because this potential is due to ionic cores, and these ionic cores are arranged in a periodic array because they're sitting on the lattice sides, right? Regular lattice sides, right? So, for instance, in 1D, I can depict it like this. So, if you have a 1D lattice, so these are your lattice sites where the positively charged ions are sitting. Okay, and then I can say that the potential seen by the electron is something like this. So it's not exactly 1 by r, but something similar. This is the kind of potential that the electron is seeing inside. Right? So at each lattice point, you have this potential. Okay. So this is what this potential is. So the property of this potential is that V at any point in the lattice VR is same as V R plus R where this capital R is no ordinary vector. This is the lattice vector. You know the definition of lattice vector. Lattice vector defines the lattice. We call it primitive lattice vector also. So R here is the primitive lattice vector that defines the Bravais lattice. So it's n1 times a1 vector plus n2 times a2 vector plus n3 times a3 vector, where a1, a2, a3 are the primitive lattice vectors, right? So R is your n1 a1 plus n2 a2 plus n3 a3. Now we are back to the module 1 of this course, right? That is, this R is a lattice vector. These n1, n2, n3 are integers, a1, a2, a3 are the primitive lattice vectors. So that's the property of our potential. The potential has the periodicity of the lattice, right? So let me write it down here because it's an important point. The lattice potential, well, it's also it's an obvious point also, right? I mean, I don't need to stress on it so much. The lattice potential is a periodic potential. And what is the periodicity? Having the same periodicity as that of the underlying Bravais lattice, right? So it has the same periodicity as that of the underlying Bravais lattice. Bravais. All right. Now comes these were trivial things, very important though. But none of these would really move you. But my job here is to move you, to shake your conscience. So suppose I go from here to here. And suppose, once again, a very hypothetical situation. There is a lattice, but there are no ions. It's a purely hypothetical situation. There is a lattice, but there are no ions. There are no positive charges. So the situation is still the same as before. We have a uniform positive background, but now we have a lattice. You know, lattice is what? It's a mathematical construct. It's an abstraction, right? How is this parabola going to change? That's the question. So this is known as, so this is our one starting point called the free electron gas model. Now the second point is, I will bring in complications slowly in steps. So my second point is where I say we deal with what is known as the empty lattice model. Lattice is there, but it's empty. Do you think it will make a difference? Of course it will, otherwise I won't pause here and ask you this question. What difference would it make? So one question is that the energy will lower. Why would the energy lower? Why would the energy of electrons lower? We are not putting any, the energy of electrons can only lower by putting in some electric field or bringing in some negative charges or whatever, or positive charges, not negative charges. Negative charges will raise its energy. So I don't think the parabola is going to shift up or down. What else can happen? It's a very fundamental question. And the answer to this question is lecture number 1 of this course. You remember what I told you in first lecture. In here, when the electron is here and the boundaries are very far, far away. I mean, the picture that I have drawn is a simplification. When we talk about a specimen, a sample, it's 1 centimeter by 1 centimeter, which is very, very large compared to the world that the electron sees around it, right? The electron is a tiny particle, or the atoms, right? So, when an electron which is not really at the boundaries, an electron in the middle, what does it see? It sees electrons around it, right? Now, if I displace this electron a little bit, not a little bit, let's say by several lattice, several angstroms, maybe I move it from here to here, okay, and then I tell this electron, please wake up. The electron doesn't know that it has been moved. Will he be able to figure out that he has been moved? He or she, I mean, I should not be associating a gender to it. Will it be able to tell that it has been moved? No, it won't be able to tell, because it's again seeing the same things, same atmosphere around it as it was seeing before, right? On the other hand, now here again you have the same electron gas, just that you have now demarcated, you have put the boundaries, these lattice. So an electron is here. So the electron knew that it was much closer to this ion than to any of these other three, right? Now, if I move it without this electron knowing that it has been moved, and I move it to some other cell, and I move it to some other cell at some other position, let's say at this position. So what's going to happen? This electron will immediately know that it has been moved, because now it's more closer to the top right corner. Previously, it was more closer to the bottom left corner, right? So that means the electron now knows that it has been displaced. So what does it mean? What it means is that the translational invariance that the electron was enjoying in the model 1 is not being enjoyed by the electron in the model 2. The electron in the model 2 doesn't have the same translational invariance, the experience of the same translational invariance that the electron in the model 2 has, right? But there is one more thing. The translational invariance is not completely broken. If you move this electron from a position into a new cell at a position which is identical with respect to its position before in this cell, relative to these 4 ions, if it is same, then again it won't know that it has been moved, right? So what does it mean? It means that if the electron is displaced by a lattice vector, then it will find itself in the same identical environment as it was before, right? So the translational invariance is broken, but you still have the discrete translational invariance, right? So here in model 1, here you have a continuous translational invariance, or you can say that the space is symmetric in this case, but in this case you have a discrete translational invariance limited to a lattice vector. Now, in this situation, what's going to happen is that the same parabola will look exactly the same, right? Now, previously we had these q values. Remember, I told you that q is not a continuous variable, it's a discrete variable. It's another thing that the two successive q points are very closely spaced, because L is a macroscopic number, it's a large quantity. But these are your q values, right? Again, you have the q values. But in addition to the q values, now because you have a lattice, you also have a reciprocal lattice vector that lives in the reciprocal space, right? So that means at a distance of, what is the reciprocal lattice vector for 1D? So you have one-dimensional lattice. Let's say we are dealing with 1D. Now don't look at it. So if it is a 1D lattice, this is a 1D parabola. Okay, then these are your Bravais lattice points. that are a distance a apart. So this spacing is a, okay, and this total length is L, and the total number of lattice points are capital N. So n times a is equal to L, where n is a very large number. In 3D, this number is of the order of Avogadro number. In 1D, you can take the cube root of it and you can get this estimate. So this is your n, right? So now this is your Bravais lattice in 1D. So the in the reciprocal space, the equivalent. So 1D lattice in 1D is r vector equals a times n times x cap, where n belongs to integer. So you put the values of n and you will generate this lattice, the 1D lattice. Now its reciprocal lattice is G, which is 2 pi by a times some integer m, right? And again oriented along the x-axis, right? So that means you have now, besides the q points that are wave vectors of the electron waves, you also have the lattice vectors, right? Reciprocal lattice vectors. So you will have here, let's say 2 pi by a, and then 4 pi by a, and so on and so forth. And similarly on this side, you have minus 2 pi by a, and so on and so forth. Right? Do you remember what's the definition of first build one zone? Do you know how to construct it? Or you have forgotten everything? The first build one zone in 1D lattice, in this lattice would be extending from where to where? Minus pi by a to plus pi by a, right? Whenever you forget that, take the origin, connect it to the nearest neighbors, and take the perpendicular bisector, right? So here is your first build one zone, minus pi by a to plus pi by a. Good. So this is minus pi by a. So I'm going to draw a line here. And here is your minus pi by a. So a line here as well. Okay. And similarly at 2 pi by a, I can draw a line. And at minus 2 pi by a. Right? So where is the first build one zone? The first build one zone is here. This is 1 minus. This is the negative half of first build one zone. This is the positive half of first build one zone. This is the positive half of second build one zone. This is the negative half of second build one zone, and so on and so forth. Right? So the second build one zone extends from here to here. This is this and this. Right? So it is present in piecewise manner, not a continuous manner. Okay, so now what I'm going to do, and you're familiar with it because we have done it before. So what I'm going to do is, you see this portion of my dispersion, the free electron dispersion, this portion, what can I do? I can map it into the first build one zone. You know, we did such mappings, right? Because the entire physics can be described by the wave vectors living in the first build one zone. So how will I map this here? Yeah, so the copy of this would be exactly this. I subtracted a g vector and I brought it here, right? Similarly, I can take this guy and map it into the first build one zone, and its map in the first build one zone will be this. And then it will go on like this, and it will go on like this. Is this clear to you? What have I done? I have taken this portion and put it here, and similarly I have taken this portion and included it here. by by using a reciprocal lattice factor, right? Is this point clear to everyone? So here is your pi by a, and this is minus pi by a. So basically any point here, if I take and if I subtract 2 pi by a from it, 2 pi by a is the lattice vector, remember reciprocal lattice vector, it is g naught, the smallest reciprocal lattice vector. From any of these q's, if I subtract 2 pi by a, I'll get this part. And same for this. In any of these, if I add 2 pi by a, I'll get this part, right? So this is the consequence of having a bare lattice without decorating it with positively charged ions. So what I can do now is I can let's not draw it right under below this because it will confuse you a bit. Let me draw it here. So I'm now drawing only the from here. So this is known as the way this is drawn here. Okay. If I don't draw these, if I don't bring them into the first build one zone, this is known as an extended zone scheme. Okay. Now, what we can do then is to have everything limited to the first build one zone because we don't need to see outside the first build one zone. So this scheme is known as the reduced zone scheme because you have reduced the entire dispersion. The free electron parabola has been reduced into the first build one zone. Okay, so I need to now lower the board. So the dispersion looks like this. And then okay. So now I can erase this middle picture. So what I have done is I have mapped this free electron parabola into this here. This is what I have achieved by introducing a lattice. The more fundamental question is, I'll come to you in a minute, is that the translational symmetry relates to the conservation of momentum, right? So in this case, the momentum of the electron is conserved, okay? But in this case, now if you multiply with h bar, the x-axis of your plots, you will get the momentum, right? In this case, you will get the momentum. In fact, we showed that. We showed that the eigenstates are actually also the eigenstates of momentum operator. But in this case, that won't be true. Why? Because you have broken the symmetry. It's no more a continuous symmetry, continuous translational invariance. It is a discrete translational invariance. So here also, the momentum is conserved, but it is conserved in a very restricted way. So the conservation of momentum, the form of conservation of momentum here will take a slightly different form, not slightly actually, fundamentally different. So this This is known as the conservation of crystal momentum. So the momentum is conserved up to a g vector. So you need to multiply, by h. You need to add a g vector in order to conservation of. So you cannot talk about the conservation of momentum of an independent electron. It will be the conservation of crystal momentum, and this is because of the broken symmetry. Okay. If there is no symmetry, not even a discrete translational symmetry, then of course even this won't be conserved. Okay. Now, we go to third model, which is known as the nearly free electron model. So what you are going to do now is you are going to turn on the potentials at each of these lattice sites. You are going to do it gradually. So you will start with a very weak potential, lattice potential, and then you can crank up the strength of that potential, right? So right now, we will limit ourselves to a very weak potential. Let's see what will be the effect of turning on the potential on this picture. Do you understand the aim? I will turn on the potential and see what will be the effect of a weak potential, a weak lattice potential on the free electron parabola. In other words, what I am trying to ask, the question that I am trying to ask is that if E naught q and psi naught q is the eigenstate of the free electron and E naught q is the free electron parabola, how is this going to change if I turn on a very weak lattice potential? This will evolve to EQ and this will evolve to psi q. Question is, how is EQ related to E naught q and how is psi q related to psi naught q? That's the question that we are asking. And do you know how to solve such problems? Using a theory known as perturbation theory, isn't it? In quantum mechanics, how do you deal with weak perturbations? So it is like a weak perturbation. So far there is no perturbation. In empty lattice model, it's a conceptual change, right? We brought in this intermediate picture because this intermediate picture is linked to the final picture. There are actually positive ions sitting at the regular lattice sites. That's not a hidden truth. That's the very naked truth. So we brought in this middle intermediate picture because I just wanted to draw this, that look, if you have a lattice, then first change that will happen is this. Now you can think of it like this, that if my perturbation is 0, you do this. I don't know if you have learned perturbation theory in quantum mechanics or not. What do? You have a potential well, you know the eigenstates of it, and then you perturb it slightly, and then you ask yourself, how are the eigenvalues and eigenstates going to change now if against this small perturbation, right? You do this, you solve such problems in quantum mechanics. So empty lattice model corresponds to the perturbation being 0. So this is your perturbation. So now you know the eigenstates and eigenvalues of the original problem, which is a free electron parabola, and you are asking what will be the eigenstate and eigenvalue, corresponding eigenstate and eigenvalue if I turn on this perturbation, right? So before showing you mathematically what's going to happen, let's try to do it. Let me give you the results first. So what do you think will happen? So up to now there is no perturbation. V is still 0. So that means we are dealing with the free V is 0 and therefore we are dealing with this. all we did is we folded the entire free electron parabola into the first Brillouin zone. And we could do this because there is an underlying lattice. And the consequence of that was that now the electron momentum is no more conserved. What is conserved is a more global momentum, which is the momentum of the entire crystal, right? Because the reciprocal lattice will also come into picture in order to conserve the momentum, right? Otherwise, how will you conserve the momentum in going from here to here? Because for both the states, the q vector is the same, right? But you do that by introducing a g vector, isn't it? Okay. So, I will give you first the results and then we will prove that mathematically. So, what is going to happen is that in the presence of a weak perturbation, okay, let me take your question because maybe it is relevant. There is no potential. That's why any of these branches are not any different from the free electron parabola. That means this is exactly E naught q. This is exactly E naught q. It's not more or less compared to E naught q. And this is also E naught q. It's just that you have folded it back into the first zone. The energies are very much equal. I mean, there is absolutely no shift in terms of energies up or down. In the limit of in the limit of A going to 0, your Brillouin zone is going to expand hugely. Sorry? So in the case of A going to 0, this will go to plus minus infinity and you are left with this branch, if you like, isn't it? I mean, if A goes to 0, this boundary will go to plus infinity, that boundary will go to minus, and you will see only this part, this portion. Isn't it so? No, so this part will remain, right? I mean, the energy goes as q square by 2m. Okay, fine. So now let me show you what's going to happen. Okay, I have to erase it. So what's going to happen is something very interesting, and we will prove it mathematically. So you will see that if the potential is very weak, please be with me because it's a very important point. Then away from the zone boundaries, when you're away from the zone boundaries, the free electron parabola is not perturbed much. In fact, it's more or less the same. So EQ is same as E naught Q when you are not very close to the zone boundaries. The only difference comes when you go closer to the zone boundaries. So what's going to happen is that this energy is going to lower and you will be here like this. And you will be not only here, we will show it that the slope of this dE by dQ will vanish. Similarly here, it will be lowered like this. And the energy of the states above, their energy is going to increase. So you will get something like this. And on this side, you get like this. And similarly, here you will get this, and then here you will get this. So what is the effect? The effect is that the potential has removed this degeneracy. There is a degeneracy here. The two states here degenerate, the upper band, and similarly this degeneracy. Okay, and you got this new dispersion. So let's draw the new dispersion. So the new dispersion then looks like this. the new dispersion looks like this. Right? What has changed? What has changed is that the energy from here to here, this energy is now inaccessible to the electrons. This energy, this band, the energies in the yellow band are not allowed because your dispersion is limited here. So you have, for this value of Q, you have an energy, you have an energy, you have an energy, and then again, for these values of Q, you have energies, but this energy range, the energy range from here to here, there is no branch. Similarly, you got a gap here. So what have you done by turning on the potential? You have introduced gaps, forbidden energy gaps. So you have electronic states in this region, you have electronic states in this region, you have electronic states in this region, but then between these electronic states you have forbidden energy regions. These regions where the electronic states are present, these are called bands. So you have band 1, you have band 2, you have band 3, and so on and so forth, and these bands are separated by the forbidden energy gap. Okay? So I am going to use nu as band index. So nu is 1 over here, this is band 1, nu is 2, this is band 2, nu is 3, band 3, and between the top of nu 1 and the bottom of nu 2, there is a gap, energy gap. Okay? So this is an energy gap where the electronic states are forbidden. This is an energy gap. And this is the same energy gap that you have seen so far in the textbooks, and always you kept wondering what this gap is. That's this gap. That's how it opens up. Okay? Now let's try to see if we can understand how we characterize materials as insulators and conductors. Suppose, but before that, because I know you are not in touch with what I did in the last 2-3 lectures, so it's my job to first revise the things. So here you have, what do you have here? Is this line continuous? No, it's quasi-continuous. What do you have here? You have Q points. These Q points. Right? We are dealing with 1D, so it's only one dimension. What is a Q point? How many electrons can a Q point accommodate? 2. अरे तो आपको शुरू से पढ़ा रहा हूँ, अब तो सीख जाओ. Every Q point takes 2 electrons. Right? A quantum state is defined by the coordinates of Q and the spin quantum number. Right? Qx, Qy, Qz, and either spin up or spin down. Right? So in this case, you have only Qx. You don't have Qy or Qz. So you have only 2 quantum numbers. One is the spin quantum number, and second the Q quantum number. Right? So therefore, the point here, this Q point, for instance, it has some value 2 pi by L times 10, for instance. Let's say it's the 10th point from here. This Q point can take 2 electrons. Right? The next one can also take 2 electrons and 2 electrons and 2 electrons. So how many electrons can I have starting from here to here if I restrict myself only to this branch below the yellow band, the first yellow band? That will be the total number of Q points from minus pi by A to plus pi by A Total number of q points, multiply it with 2. That will be the number of electrons that I can accommodate. That is the number of electrons that I can accommodate in this band. If I get those many electrons, this band will be completely full, and above this there will be a forbidden gap. So, what will this be? Will this be a metal or an insulator? It will be an insulator, because this band is completely filled up to here, and then there is a gap, and if the gap is very large, then of course these electrons cannot access these states, and therefore your material is insulating. On the other hand, if I give you only half the electrons that you can fill in this band, then you will fill this band only up to half the energy, and then you have these empty states above it, and then it will be a metal, right. So, first let us figure out how many q points are there between minus pi by a and plus pi by a. Who will tell me? This is the picture. The length of the lattice is L. The lattice points are spaced at a distance a. So, what will be, so if you look at this, q is 2 pi by L. So, q is 2 pi by L, which is equal to q, meaning delta q. The separation between any two q points is this, which is same as 2 pi by NA, right. So, in going from here to here, what is the distance between these 2 points? 2 pi by A, isn't it? 0 to pi by A, 0 to pi by A, 2 pi by A. So, delta q is this, separation between any two q points is this. So, therefore, over a length of 2 pi by A, how many q points will be there? N, capital N, isn't it so? Because the spacing is 2 pi by NA. So, therefore, on a segment of length 2 pi by A in the reciprocal space, on a segment of length 2 pi by A, the number of q points will be N. That is the same as number of lattice points, or the same as number of atoms, right. So, the number of q points is equal to capital N. Now, suppose in your hypothetical 1D lattice, each lattice point has a sodium ion. Sodium ion gives how many electrons to the conduction band? Only one. So, therefore, how many electrons you will have in your lattice? As many as the number of sodium ions. How many sodium ions do you have? Capital N. So, therefore, how many electrons do you have? Capital N. So, you have as many electrons as the number of q points. You have as many electrons as the number of q points. Number of q points are N, isn't it so? Number of q points are N, and number of electrons are also N, but each q point can take 2 electrons. So, therefore, this band is fully filled or half filled? Half. Therefore, it will be a metal or a insulator? You have answered the question. It will be a metal. So, in the case of sodium, this band will just be half filled, and a half filled band. So, the states up to here are filled, up to wherever you can reach half the value, and all these states up to here are empty, right. Now, let's cook up another material where each atom gives 2 electrons to the conduction band. In that case, number of electrons that are available to you are how many? 2n, right, and number of q points are also n. So, the number of quantum states are 2n also, right. Quantum state refers to q point times the spin degree of freedom. So, in that case, the band will be filled up to the topmost point, and so if you apply an electric field, there are no quantum states available where the electron can excite itself to and start conducting electricity. right, because there are no states here, because there is no dispersion here. Dispersion is absent here, right. So, that is the essence of the band theory. Now, in the next lecture, my job will be to put this entire thing more rigorously in a mathematical framework using the perturbation theory. So, we will be using, first we will be using the first order perturbation theory, and you will see that the first order perturbation theory has absolutely no effect on the free electron parabola. Then you will use the second order perturbation theory, and you will see that the second order perturbation theory does explain things nicely, but the second order perturbation theory fails because of this degeneracy here. So, then you will have to use the degenerate perturbation theory. When the states are degenerate, then you use a perturbation theory known as degenerate perturbation theory, and then you will see that this degeneracy gets lifted. But do not go by the jargons, it is a very simple thing, you will enjoy it, you will learn it very, very fast, right. But this point is very important, more than maths. Maths you will learn anyways on your own. This whole thing that I did, this progression going from free electron model to the empty lattice model and then the turning on the weak potential, this is conceptually very, very important, and then to get metals and insulators, right, depending on the filling factor. So, we are going to call this N as the filling factor. So, in the case of sodium, for example, the filling factor is 1/2. In the case of our hypothetical material, second material, the filling factor was 1. So, the entire band got filled, right. And then if you have some material where the number of electrons per atom is 2.1, for instance, then you would have filled this fully and you would have filled 10% of this band. So, you have lots and lots of empty states above it. So, it will be a very nice conductor. Yeah.
So, sir, these are the energy levels, and the which one is conduction band? Like these are all our energy levels.
Exactly. So, if you are in the case of sodium, this itself is the conduction band, right. In the case of the second metal which I talked about, this is now your valence band because there are no conduction electrons, or in other words, the conduction band is completely filled. So, then you have this. So, this is again not a very complete picture of the band theory. This is just a beginning, you know, a bare minimum theory. Yeah. Yeah. Just one last point. So, I stressed on this point that here the dispersion becomes almost flat. The essence of that is that the electrons that are here, that are present here, they won't conduct because they will form a standing wave. And in fact, in tomorrow's lecture, what I am going to show you also is that at the zone boundaries, you form standing waves. So, what that means is that you have an electron whose wave vector is q, and then you ask a question in the presence of a potential, will it scatter into a new state q prime, then what would be the matrix element m q q prime, right, because this matrix element, the square of this matrix element mod square will give you the probability of such a scattering event, right. And you would see that such scatterings happen only when q and q prime are related by this relation. And have you seen this relation before, earlier? Yes, you have seen this in the context of lattice, right. The only difference is that here this was the wave vector of the photon, the photon that was coming externally into the lattice, right. So, basically it is the same Lave condition, except that instead of the photons, the light wave, you have the electron wave that gets reflected at the zone boundaries and forms standing waves, and that is why their group velocity becomes 0, because the dE, del E, del Q at this point will disappear, will vanish, right. That is the essence. Okay, we stop here.